So in our previous class where we got an introduction to line integrals, there were a couple of examples where it was sort of tantalizingly possible that the line integral of a vector field from a point A to a point B depended only on the point A and the point B and did not depend on how we got from point A to point B. We could have gone there along a straight line, or we could have done a couple of straight lines that took a detour, or maybe we could take a curve instead of a straight line. As long as the starting and ending points were the same, then it didn't matter how we got from point A to point B. And at the time we said, well, is this something that's always going to be true, or is there some special property of vector fields that's going to make that true? And so today is our day to answer that question. And so what we're going to get in this section 12.4 is a study of when is a vector field path independent, so that its line integrals don't care how we get from A to B, but just what is A and what is B. And then for those vector fields, we have a really powerful tool called the fundamental theorem of calculus for line integrals that lets us, instead of evaluating a path integral, we can just find an antiderivative for our vector field, an ungradient of our vector field, and then evaluate that scalar potential function that we get and the ungradient at the endpoint and at the starting point, and subtracting the two to get the value of the definite integral. So we call this a fundamental theorem for line integrals for what I think is a pretty good reason. And the reason is this, that if I have a gradient vector field and I'm trying to find a path integral for a gradient vector field, so if f is a vector field that's equal to the gradient of some scalar potential function, then if I wanted to compute the line integral of this thing along some path c, if I wanted to compute it directly, I would have to do this nasty thing that we did at the end of our last class, right? Where we take our parameterization for our curve and we evaluate the vector field along that parameterization. We take the dot product of that evaluated vector field along the velocity vector to our parameterized curve, and then we have some huge integral, which is a function of t. We integrate it from t equals a to t equals b, and then it spits out our answer. But here's the good news. And the good news is that if f is the gradient vector field of some scalar potential function, then I can sort of replace this f here with the gradient of h. Put a little vector over the gradient symbol to remind us that that's a gradient, that's a vector field, right? And if we sort of squint at this quantity that I have over here, that's my integrand, I have the derivative in the form of the gradient of a scalar potential function. So I have the derivative of h evaluated at r of t. And then I have the dot product of that with r prime of t. If I were to sort of expand out what this looks like, this would sort of look like whatever is my, let's give our gradient vector field some components. Let's say we're in 3 dimensions, so that everything here is a function of x, y, and z. But what we're doing here could work in any number of dimensions. So let's say that the components are p, q, and r for my gradient vector field. So then what I have in here, when I evaluate my gradient vector field on the parameterization r of t, I get p evaluated at r of t, comma q evaluated at r of t, comma r evaluated at r of t. And then I'm taking the dot product of that with the velocity vector r prime of t. So this is what would be r1 prime of t, r2 prime of t, r3 prime of t. And maybe another way to think about what r1, r2, and r3 actually are is that they're the x, y, and z component functions for my parameterized curve. So I'm just going to call these x prime, y prime, and z prime. Just to kind of, oops. Except, hold on. I want to be actually really careful here that if my, so p, q, and r are the components of my gradient vector of h, except that means that by definition of gradient, right, p is just the h, the partial derivative of h with respect to x. So I'm going to replace p here by the partial of h with respect to x. Partial of h with respect to x evaluated along r of t. And then my q is the partial of h with respect to y. And my r is the partial of h with respect to z, evaluated along r of t. And when I take this dot product, what I end up getting is the sum of the products, right? And so I'm going to have dh dx, the partial of h with respect to x, times x prime of t, I'll call that dx dt, plus the partial of h with respect to y, times the derivative of y with respect to t, dy dt, and then the third term is going to be the partial of h with respect to z, times the derivative of z with respect to t. Oops, that's ordinary derivative, z dt. And so here I'm going to pause and ask, where have we seen an expansion of an expression that looks like the one that I just wrote down here? What does this resemble? This looks like the right-hand side of an expression that we last saw when we were looking at the multidimensional chain rule. Right? And so the multidimensional chain rule would tell me that what we're looking at over here on the right-hand side is we're really looking at, and this is the big observation, this thing is nothing more than the time derivative of h of r of t. Exclamation point, exclamation point, right? That's what that thing is, right? According to the multidimensional chain rule, the time derivative of h of r of t is going to be the x derivative of h times the derivative of x with respect to t, added to the y derivative of h multiplied by the derivative of the y component with respect to t, plus the z partial derivative of h multiplied by the time derivative of z. So this is why we call it the fundamental theorem of calculus. The thing that we're about to invoke here is that we're going to directly invoke the ordinary fundamental theorem of calculus to simplify this integral that we have over here. So this is supposed to be the integral t ranging from whatever is my starting point to whatever is my ending point of my parametrized curve, a to b. But then what I have as my new integrand is I have the time derivative of h of r of t. And I'm integrating the derivative with respect to t of some function, and I'm integrating that with respect to t. Well, what happens when I integrate the derivative of a function? Invoking the ordinary fundamental theorem of calculus, if I want to find the integral of the derivative of a function, well, I want the antiderivative of the derivative of my function, and I want to evaluate that antiderivative at the starting point and the ending point. And so the antiderivative of the time derivative of h of r of t is just h of r of t. And I'll evaluate that from t equals a to t equals b. And so what I'm going to get here is h evaluated at my endpoint, which is r of b, minus h evaluated at my starting point, which is h of r of a. And so there it is. We can compute a path integral of a gradient vector field by just finding the scalar potential function h, of which our vector field is the gradient, and then just evaluating that scalar potential function at the endpoint and at the starting point of my curve, and just subtracting the two. And so we can see from this equation here that because this ending answer doesn't depend at all on how we got from point A to point B, it only depends on the value of the scalar potential function at the point A and the point B. That's what tells us that this integral is path independent. Right? It doesn't care about how we got from the starting point to the ending point. It only cares what is the difference in the scalar potential function's value between the starting point and the ending point. And so the recipe for using the fundamental theorem of line integrals to evaluate a line integral of a gradient vector field is just to find the scalar potential function for that vector field, and then evaluate that scalar potential function at the starting point and at the ending point, and then subtract the results. So that's where I want to throw it over to you to get some practice invoking this fundamental theorem. So the activity number 2 in this section gives us a couple of different examples to do. Let's just do example A to get ourselves started. So example A asks us for the path integral of the gradient of f, where f is this scalar function, 3xy squared minus sine of x plus e to the y. And C, the curve, is the top half of the unit circle oriented from negative 1, 0 to 1, 0. So let's just do part A in your group, and then we'll use that as a way to move forward. So in our first couple examples, we figured out that we can find the path integral of a gradient vector field if we know the scalar potential function. Then all we have to do is evaluate that scalar potential function at the ending point and at the starting point and subtract the two. So for the integral of the gradient vector field of this function from along the top half of the unit circle oriented from -1, 0 to 1, 0, we can totally just plug our ears and say, we didn't hear the unit circle part. We didn't hear you say that. We only heard that the curve started at -1, 0, -1, 0, and it ended at 1, 0. And so evaluating the scalar potential function at 1, 0, and then at -1, 0, and subtracting the results will give you the value of that integral. I think there's maybe a algebra issue with this evaluation here. Sine of 1 minus the sine of 2 is not the same thing as minus the sine of 1. But anyway, we'll bypass that for just a moment. And then the second example here was the same deal, just with a function of 3 variables, a scalar potential function of 3 variables, evaluated at the ending point, subtract the evaluation at the starting point. And so it didn't matter that C was a helix. It didn't matter how we got from point A to point B. It only mattered that we got from point A to point B and evaluated the scalar potential function at those 2 points.